Friends, in this video, I am going to explain about the momentum thickness. So, I am Sushan Lal Babu, Assistant Professor, Aerospace Division, Karunya Institute of Technology and Science, Coimbatore. So, momentum thickness, in the previous videos, we discussed about the boundary layer formation and the displacement thickness. So, what is displacement thickness? The thickness, or the thickness which the fluid layer shifted in the direction normal to the surface in order to compensate for the reduction of mass flow rate is called displacement thickness. To compensate for the reduction of mass flow rate is called displacement thickness. Okay, then momentum thickness, you can say that. To compensate for the reduction in the momentum flow rate is called momentum thickness. So next, if it is energy thickness, means what? To compensate for the reduction in the energy rate of flow of energy is called energy thickness. So why it has to compensate? Because of the formation of boundary layer. Since boundary layer is formed, velocity got reduced within the boundary layer, so that effect will leads to loss in mass flow rate, loss in mass flow rate, loss in momentum flow rate, loss in energy flow rate. But our conservation law states that mass flow rate has to be constant, energy flow rate has to be constant, momentum flow rate has to be constant. Constant between what? Between our reference inlet and reference outlet. If 5 kg is entering per second, then 5 kg has to move out per second, even if there is boundary layer formation or not. Mass flow has to be constant, momentum flow has to be constant, energy flow has to be constant. So definitely, if velocity reduces accordingly, velocity, because mass flow rate, if you write the equation of mass flow rate, what is the value of m dot? M dot is actually what you can write it as, again, m dot is nothing but density into area into velocity. So if velocity decreases, then m dot will decrease, but conservation law states that m dot shouldn't decrease, it should remain constant. So to keep the mass flow rate constant, it has to shift some amount of thickness called displacement thickness. Similarly, to keep the momentum flow rate constant, the boundary layer or the fluid layer has to shift a small amount or small thickness theta to keep the momentum flow rate constant. So that is here I am going to explain. So with this figure, easy to understand. Actually, as earlier in the previous video also I explained this, and we are taking a cut section. We are taking a cut section here. Okay, so if you view it from the right side, you are viewing from right to left. From the side, you can see this box, rectangle box. You can see this rectangle box from of if you are viewing from the side, right side to left. If you are viewing, you can see it as like a rectangular box. Okay, so and what here we did is, actually, what is m dot I wrote. M dot is nothing but rho into a into e, but p dot is nothing but, what is p dot? One minute. Sorry. Okay, yes. What is p dot? P dot is nothing but m dot into velocity. Or what is p? P is nothing but m into mass into velocity is the momentum. Then p dot is nothing but m dot into velocity. M dot we know. So how, if we know the m dot through this small strip, we can calculate the momentum, rate of change of momentum happening through that strip. What is that? dpu with p small u dm m, this is a dot only. Okay, into u, that is okay. So how we can write? Rho into u into, this is area into velocity. This total will be what? M dot u. Okay, m dot u into u, that is rho u square b dy is the p, change of momentum happening through a small strip. If then there is no boundary layer formation, how, what, at what velocity this will move through that dy? Flow will happen with velocity capital U. So then we will replace that, will get rho into u into b dy. Okay, so what is the loss in momentum? So this will be larger, this moment, this will be larger. Okay, this will be larger, And what is the difference? Difference is nothing but dp into dp is equal to difference is equal to dpu minus dpu, that is equal to rho b u minus u square dy. Okay, if you integrate it, because this is for a small length dy, and if you integrate from the 0 to delta, you will get the total change across the, so p becomes dp becomes p, and the equation becomes like this. Okay, simply we are okay. Here what we are doing is that we will take u square outside, then u square outside means u by u minus u square by capital U square will come. Okay, then next is so momentum loss happened, but that has to be added somewhere, then only the momentum become constant, no? So that is added somewhere by shifting the fluid layer by a thickness theta. Okay, so what is the change of rate of change of momentum happening through this area? That is nothing but m dot into theta. Sorry, m dot into capital U. What is m dot? M dot is equal to density into uh, uh, b into area, means yes, this is area of this part region. So this is b. So b into, so this is b into theta is the area. So that is area into, so velocity is capital U. So capital U velocity into, so p means we have to multiply again with u. So that is p rho b theta u square will come. Okay, then we have to equate. If we equate this value, so this is what we compensated. So both will be equal. What reduction happened is compensated through this region. So rho b theta u square is equal to rho b u square. This 1, this is 2, 1 equals 2. So from that equating we will can this rho b u square will cancel out, and only theta will exist. That is 0 to delta. These things where everything cancels, rho and b and u square, yeah, cancel out, and you can see you will get theta is equal to 0 to delta u by u 1 minus u by u dy. That is momentum thickness. So theta is the distance, it has to be shifted, the fluid has to be shifted in the normal direction to the surface. Okay, this is the surface, and theta is shifting in this normal direction. Okay, this much theta, this much distance is shifted to compensate for the, how much thickness it has to shift to compensate the loss in momentum, that is theta. How much it has to shift in the normal direction to compensate for the loss in mass is called displacement thickness. How much it has to shift uh, in the normal direction to compensate for the energy loss is called energy thickness. Okay, here we have explained momentum thickness. Thank you.